I think we left off here. Is that correct? Good. So C++ supports multiple inheritance of implementation. C# and Java don't. You don't use multiple inheritance a lot. At least you don't use multiple inheritance of implementation a lot, but there's a few places where it can be really useful. There's something called mix-ins where we represent, maybe we have a product line. We work for a company that has a product line with a bunch of variations. And so if we represent behaviors of that product, individual behaviors with individual base classes, then we can say we want this version of the product to have these behaviors, this version of the product to have these behaviors, this version of the product to have these behaviors, and simply get those variations behavior just by choosing the right base classes. So behavior A is given to us by base class A, behavior B given to us by base class B, behavior C by C, and if we want behavior A and C, we derive publicly from A and C. Great idea. Works fine, except. Okay. Now, Java and C# chose not to support multiple inheritance of implementation, and we'll see why they might have made that choice. So I prefer to have it, but it's not without its issues. So here's an example. This is the IOStream hierarchy. And in the IOStream hierarchy, there's a base class IOS which can handles errors and formatting. And from that, we derive iStream and OStream. And IOStream does a multiple inheritance of iStream and OStream. Doesn't do much more than combine the two. So that's a example of the use of multiple inheritance, a practical example of the use of multiple inheritance. And the way we implement it, just class D, colon, public A, comma, public B, comma. This is a set, so that'll become clear in a minute. We're going to kind of focus on the fact that it's a set. If member MF of A has the same signature as a member of B, they both have a member function MF, then there's an ambiguity. If I call D, my derived class, an instance of D, D.mf, there's an ambiguity. Do I mean A's MF or do I mean B's MF? And the compiler will refuse to build it because of that ambiguity. We can resolve it by saying D.A colon colon MF or D.B colon MF, and that resolves the ambiguity. Great, problem solved. Well, maybe. So I'm going to skip over this slide. Suppose we have this situation where B and C each derive from A and D derives from multiply from B and C. Okay? Then remember that A is inside B and A is inside C, and B and C are each inside D. I showed you that last time. They literally are inside. So that means we have a situation like this. Here's D with its B and its C, and each one have an A. And D will initialize B and C, and B will initialize its A, and C will initialize its A. And from a correctness point, that's fine. No problem. But I do have redundant stuff here. All of A is repeated in both places, and that means that that means that on one hand I have all the signatures of this that are publicly accessible to me have to be disambiguated as a B signature or an A signature, and I also am duplicating that storage. So neither one of those are particularly attractive. So again, you know, when we construct a D, D constructs B, B constructs its A, D constructs C, and C constructs its A. Now, there is a way to make A coalesce into one object using virtual inheritance. A couple of things I don't like about it. One is that I'm overloading the word virtual. So virtual applied to a function means one thing. Virtual applied to a class for inheritance means a totally different thing. Has almost nothing to do with virtual applied to a function. Totally different behaviors. What this does, if I declare B deriving from A as a virtual inheritance and C deriving from A as a virtual inheritance, now when D derives from B and C, and this doesn't need to be virtual, then I have only one copy of A. And you say, great, problem solved. No ambiguity. It's correct, there is no ambiguity. No duplication of space. Perfect. Problem solved. But suppose that B needs its version of A to be initialized one way, and C needs its version of A to be initialized a different way. They're both correct classes. Now, D can correctly inherit from B and C, no problem. That's correct code. So I can break correct code with correct code. A initializes, C initializes its A correctly, B initializes its A correctly, D inherits from B and C, but there's no way, if these guys need different initializations of A, there's no way that D can supply both. It can't. And the language does say that A is initialized by the most derived object, by D. So I can break correct code with correct code, and that is not a good situation. Does it happen all the time? No, very rare. Okay, but it can. So this slide says just like what we said before. Now, here's how I initialize these classes. So B initializes its A with an initialization sequence, and here D, and so, the same for C. So D initializes A and B and C, and B's initialization of A is ignored. C's initialization of A is ignored. We use D's initialization of A, and that therein is the problem. You know, if they have exactly the same initialization, no problem. But it doesn't fail to compile if they don't, which it should, in my opinion. If I were designing the language, I would have refused to compile any multiple inheritances that had any ambiguity at all, so that you couldn't have that dreaded diamond. It wouldn't accept it. To me, anytime you have that ambiguity, that's a design flaw. For the kind of mix-ins that we'll talk, we won't talk about mix-ins today other than just in passing, but I will illustrate it on Tuesday next week. Multiple inheritance is very useful, but if you don't make those bases unique, non-ambiguous, then it's really a design flaw in my opinion. And I think the compiler should have failed to build it. But this is a choice that Stroustrup made, and that's the way it works. So, you know, Java and C# had a reason for only accepting inheritance of implementation from one class and then multiple inheriting interfaces. Okay, and you could, you know, in your designs, you could design like you do with Java and C# for that kind of a case, so that you inherit multiple interfaces and then you compose, or in the case of Java and C#, you're aggregating instances of the classes that are implementing those interfaces. Okay, so you can make it work, but it's, you know, more stuff, more parts, more moving parts, and more moving parts is always not a, you know, you want to avoid, you want to have as few moving parts as possible in a design, because our designs get, as you know from Project 1, our designs get complicated in a hurry. Okay, and that's the way professional code. That's Project 1 is very typical of what you'll, you know, the kinds of things you'll be facing when you do professional code. Okay, so let's look at some code. Yeah.
Last me remind you about compound object creation.
Yeah, I'm gonna talk about compound objects today. So I have here 3 pieces of code. I'm going to skip over demonstrate composition so that we have time to do the compound objects. This is fairly straightforward. It's worth you taking a look, but demonstrate these inheritance examples. We'll see some interesting things, some things you need to be aware of. So let me pull up deminherit. So here's deminherit. So let's go to deminherit 1. And let's set this as the startup. Now, I have a base class. Now, all of this code in deminherit it's demo code. The objects themselves do almost nothing. So I might have an assignment operator that really doesn't assign anything because there wasn't any member data to assign. But what I'm showing you is when things are called, you know. So don't get much concerned about how the data is handled, but there are things we need to look at. So here's our base. We have a default constructor, a copy constructor, a destructor, and a base assignment operator. Here's my derived class, derived from base. How many member functions does derived inherit? Can I get this all on one screen? Nog, can you see that? You can see that okay? I can't see that from here. How can you see that? I'm going to go to the bigger form. So, my base had constructors, destructor, assignment operator. So how many functions does my derived inherit? Any other opinions? None. You're right. Constructors, assignment operators, and destructors are not inherited, right? They are created when needed by a class if they're not declared in the class. This inherits none, but it has potentially 4. Void construction. It wouldn't have a void construction if I had declared any constructor in the derived class, but like a promotion constructor, for example, but I didn't declare any, so it will have a default constructor, it'll have a copy constructor if I'm doing any copying, it'll have an assignment operator if I do any assigning, okay, and it'll have a destructor. So I didn't give this guy any data, but this guy I gave data. So actually, this class, if I measured its size would be the size of a pointer because it needs a pointer to its virtual function pointer table. And this class's size will be the size of a char plus an int plus a pointer to its virtual function pointer table. Okay, so Now, I've got enunciators for the base, you know, the void constructor is announcing itself, the copy constructor is announcing itself, the destructor is announcing itself, the assignment operator is announcing itself for the base class. And because I don't have those, haven't implemented the derived classes, obviously there's no enunciation for the derived. So now let's run this. So my first executable statement of main is a void construction, sure enough. Second, notice in a second, no assignment was called. If my assignment operator had been called, it would have announced itself. So there's absolutely no assignment here. This is one operation, a copy construction. Third statement is an assignment, and I call the assignment. Now, in the fourth, I am constructing a derived object, and notice the base void constructor is called. In the fifth, I do a copy construction, and notice the base copy constructor is called. In the sixth, I do an assignment, notice the base assignment operator is called. So this is proof that the compiler is doing a base-wise and member-wise operation. So the default construction is doing a default construction on the derived default construction is doing a void construction on its base, because here it is being, in the fourth statement, here it is being called. And the derived copy construction is the implemented, the compiler-generated derived copy constructor is doing a member-wise, you know, base-wise and member-wise operation, copy operation. So it is copying its base part. Here it is, base copy constructor called. Same for the assignment operator. So that's proof that the compiler-generated operations apply base-wise to each of its bases, that operation to each of its bases. It calls that. If it's copy, it calls a copy on each of the bases and on each of the data members. In the dim comp, we would have, I don't remember whether I showed that or not. But anyway, enough. Now, notice I say compiler is not going to allow us to assign this base to the derived. Why would it make that rule? Why wouldn't it allow that? Almost certainly there is more information in the derived, more data to be assigned than there is in the base. So what would the compiler is saying, this can't be, you know, there's no way to initialize that derived part out of the base, and so I'll disallow it. Now, I could write a promotion constructor that would promote a base to a derived, and the compiler will very happily, it'll look at this, see type mismatch, and say, aha, but there's a way to resolve it by calling that promotion constructor. But we're faced with the same problem. How do we operate on that, you know, how do we specify what those derived parts are? We can't. We have no basis for it. So the compiler won't do that, but the compiler will very happily assign a derived to base. Without any coercion, very happily do that. And the reason is that D2 has a base part, and so this just slices the base part into the base of B1. It's called slicing. Okay? Compiler will always do that. We'll never do this unless we force it to. And that makes sense. Okay. Now let's go to dem inherit 2. In dem inherit 2, there are two serious problems, which we will resolve in dem inherit 2b. So here's our base, pretty much the same as we had before. Here's our derived. Now we're implementing the void construction, the copy construction, the destruction, and the assignment operator. Here's base, base. All these base operations are the same as the previous example, so let's just skip over it. Here's the derived construction. Let's focus on the copy construction. There's a serious problem here. Does anybody see the serious problem in this code? I'm copying the derived part, but I'm not copying the base part. Once I take over definition of that operation, the compiler won't generate one, and so it does what I tell it to do. If I take over implementing that operation, it does exactly what I tell it to. And I told it to copy over the value of the derived data, but I didn't tell it to do anything with the base data, and so it doesn't. Same for the assignment operator. We have exactly the same problem with the assignment operator. So here, in the assignment operator, all I did was assign the derived part. Compiler will not generate a base assignment operator for me. I implemented this, so it trusts me that this is what I want, and it's going to do exactly what I told it to. So now, let's run it. So, all the base operations are fine. Now, the fourth operation, executable statement of main, base void control called, derived void control called, that's fine. Now let's look at the fifth statement of main. Base void constructor called, derived copy called. Base void called. So the compiler has to call an operation on that base part, has to, but I didn't tell him what to do. And so he called the void constructor. His default reaction, let's call that. Could it have inferred, because I'm doing a copy, that it should have called the copy? Yeah, but it doesn't. Maybe 2 or 3 standards from now, that inference will be, the compiler's type inferencing is usually only, very, very local. It doesn't do any extended analysis to see if this, what it should do, because that's expensive. It takes time. And the whole idea is to compile. C++ was built to, designed to build really big systems that need to run really fast, and so both compile times and run times, the goal is to make them as fast as possible. So that's a problem. Now let's look at the assignment, sixth statement of main. Sixth statement of main, the derived assignment operator was called, but we can see that the base was not called because it had an enunciator. If it was called, it would have announced itself. Two serious problems. Let's see how we fix them. So we're going to fix them in the next example. Okay, so the base classes are the same. So now let's look at the derived. Whoever is talking, would you not talk, please? So let's look at the derived. So derived void constructor hasn't changed. Here is the derived copy constructor. So now I am initializing base D. And this will work correctly. I'm initializing more data as well. It still would have been correct if I put it here, but there's a reason. What happens here is this is a construction. If if this was some object and I didn't initialize it here, I just set the value down in the body, what would happen is it would have a void construction here, and then I would reinitialize it again. So you're wasting CPU cycles. It's more efficient to initialize it, and this is a correctness issue. So you should always favor initialization sequences in your constructor. Always favor it because it's correct. And you can say, yeah, but there's only a few cases where I get into this kind of problem, which is true. Only a few cases, maybe one out of every 15 classes I write, I'll get into this kind of problem. And so you got a choice. You can routinely not use initialization sequences. Try to remember, and you will forget on that 17th time, okay? You'll forget. But if you always use initialization, A, it doesn't take any more code, B, it's faster, and C, it's always correct. So I always use initialization sequences. Now, there's one exception to that. I never do on void constructors, because void constructors are correct, and it's, so you don't need to do anything, because it's void, so why tell it, well, you got to do void. But for everything else, use initialization sequences. Really, really, really important. So that fixed that problem. Now let's look at the assignment operator. So here, I have to do the base assignment. So how do I do that? Remember that you should always have this statement: if I'm assigning to myself, then don't unnecessarily burn up CPU cycles. But a lot of times I may be deleting some stuff, and I can get myself into trouble if I don't check. But here, what I have to do to assign the base part is just say, I'm using the assignment operator, but I'm casting this pointer to a base type. And so what that means is that's going to call the base assignment operator. And all the base assignment operator knows about is assigning the base part. So that's exactly what I've done. I've assigned the base part, and now here I've assigned the derived part. So always in a derived class, when you implement an assignment operator, you assign the base explicitly, and then you assign the derived. When you're constructing, you initialize the base, and then you initialize the derived part. Always. So let's run this and see how it works. Fantastic. So I got to get out of full screen. So the base operations are fine. So let's look at derived. So here's the fourth fourth executable statement of, wrong one. Do inherit 2b. So now, in the, oh yeah, that was okay. Fourth executable statement, void, void. Here comes the fifth. That's where the error was. Now, it's base copy, derived copy, because I told it to. Use the base copy. And here's the assignment, the sixth. So in the sixth statement, derived assignment called, base assignment called. Yes, correct. Okay, that's what you got to do. Okay, piece of cake. Now, let's see what I'm doing in Dem Assignment 3. One of these I want to look at and one I don't. Let me remember. No, we don't need to look at this one. This was just a... So I want to look at Dem Inherit 4. No, Dem Inherit 4. And set this as startup. So my base is identical to the previous examples. And here my derived, I have 4 functions. I have a fun1 that accepts a base by value and returns a base. I have a, now this is in my derived class, I have a fun2 that accepts a base and reference and returns a base reference. And you'd have to be careful. Anytime you return a reference, you've got to be really careful. That's always a flag that says up, because if I'm returning something I created in this function, it's no longer valid. As soon as the user gets his hand on it, it's no longer valid. So this would either have to be something on the heap, or it would have to be, in this case, I just passed this B through to that B. Here's a derived 3, pass by value, return by value, pass by reference, return by reference. So we want to focus particularly on fun3. Let's run this and look at the operation of fun3. So here's my main. And the 11th statement of main is fun3. Now, let's look at its function. Here's fun3. Simple little, not much going on there. Right? Not much going on there. Oh yeah? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 operations. What? Sure. Remember that this is a composite object, so when I pass my D in by value, and so I'm copying D, which also copies a B, I create a temporary D as a copy construction, as a copy construction, so I am copying a derived and a base, and then I return it, and so by value, so I'm copying a derived and a base, and then I'm destroying the internal temp, so I'm destroying a derived and a base, and now when I come out to 11th, I'm assigning a derived, so I'm assigning a derived and a base. So when you have composite objects, you got to be really careful. So here, you'll see my code littered with pass by const reference. Pass by const reference. Pass by const reference. Not value. I return by value because in most cases you're forced to. And you say, gee, that's expensive, but suppose I move. Now that's no longer expensive because I'm just transferring ownership of those resources. I'm not copying any resources at all. I'm just transferring ownership. Doing a couple of pointer swaps. Bam. Okay? So it's not at all uncommon a thoughtful professional designer will write some code and a average skilled developer writes the same code and it runs 10 times slower because of that. Not at all uncommon. But what it really takes is just habit. Always pass by const reference if you possibly can. Always. And if you don't provide operations that the compiler will, so I don't provide any copy construction, assignment operators, or destructors, the compiler will generate move. So when you're in a move situation, I'm passing this data structure that I'm building or something out by value, that the stuff inside that function is temporary. The compiler knows it, and so it does a member-wise move. Now, if any of the classes, those parts, the bases and the data members, if they don't provide a move constructor, then they will be copied. But as long as they provide move, the compiler generated just move. So what that means is that if you don't provide those operations where you shouldn't, I keep telling you, if the bases and data members have correct copy, assignment, and destruction semantics, you shouldn't supply those operations. Here's one reason why. You don't have to write those moves. Compiler will write them for you. And now everything will run fast, blazingly fast. Bam! Okay. So, I have a mission for you. I want you tonight to go home and sit down with the debugger and walk through this code with the debugger and walk through this code with the debugger. And you'll see what I said is true, that, you are calling all those functions, if I say type instance equals some existing instance, that is one operation, a copy construction. Convince yourself of that. Be skeptical. I don't believe that. Sit down with the debugger and watch what's called. Okay, now I want to talk about, thanks to Naga for reminding me, I want to talk about compound objects. So that is in repository CPP. So let's go open. Yeah, I have it right here from an hour ago. An hour and a half ago. So remember this diagram. Let's go to the preceding lecture. And I showed you this diagram. Class form, logic form, and physical form, object form. Okay? We're going to, this compound object code implements this. It has a C, has a B, has a D, has a U, and has a class. Okay? So, here's my class C. Now, none of these classes, every one of these classes, if my memory serves me right, every one of these classes would work just fine if I didn't write any constructors or destructors. Because they have strings, which are containers, and primitive data, nothing else. So I don't need to write them. But I wanted to write them to show you how to. This is a template. I first wrote this for myself to make sure I knew how to write all that syntax, and now it's for you. So my class C is the guy that's going to be composed by the base, and so I have a copy construction, copy assignment, and I'm doing the if this and so on. And again, this is a demo, so there may not be a lot of stuff. I might write an assignment operator that doesn't really assign any values at all because there weren't any values in the class, but it's here to show what's being called. Now I have a move construction and a move assignment. And notice in this move, this class C held a string. This class C held a string right here. So now in my move construction, I am using a initialization sequence, and I'm telling it standard move, C.name. Okay? Compiler doesn't do it. The compiler knows if I put D in a function and return it by value, the compiler knows that I'm going to move out D. But it doesn't do the extended analysis to say, oh, that implies that we move B, oh, that implies we move C. If I don't say so, it'll move D and copy B and copy C. So you got to say so. There's one reason why you don't want to write these if you don't have to, because this is a little bit of work. If the bases in the member data have correct value semantics, copy, assignment, and destruction, don't write them. But, so here's my my move construction. Here's my move assignment. So in the move assignment, where in the assignment operator I said name underscore equals C.name, now I say name underscore equals standard move of C.name. That moves it. Okay? Now here's B. So the copy constructor for B, again I'm using initialization sequence, okay? The copy assignment, I say C equals B.C, okay? And now in the move construction, I say B, C colon standard move of B.C. And in the assignment operator, I say C equals standard move of B.C. Yeah, okay, yeah, makes sense. And I have a virtual G and a virtual destructor. We'll see why we have the virtual G here. I have yet to explain why you need a virtual destructor. You do. Any class that has virtual methods needs a virtual destructor, but I will explain that on Tuesday. Okay, that's coming up on Tuesday. Here's my U class. This is a using class. And so I provided a copy constructor and a copy assignment, move construction, move assignment. Here's my derived class, D. So now D copies B, and now D, in the copy constructor, D didn't have to also copy BC because B does it. Just by invoking the B constructor, that copies C. Okay? So, and that's, you always want that layering, you want to make sure that layering works, that you don't need to know. This guy doesn't need to know the internals of B. All it needs to do is call that B constructor. And assignment, same way here, B colon colon operator equal D. So I am slicing the derived object to its base because I'm using a base operator, and that's all the base operator knows how to do is assign the base parts. So I'm slicing this D's base into my base. Okay? And I didn't have any data members here. If I did have data members, then I would be assigning my data members before I returned. And here's my move construction where before I initialized B of D, now I say B of standard move of D. Okay, this is the D object, so I'm copying this D object. And so now when I initialize B, I'm initializing B on D, which is doing a slice of D, but now I've got to move that slice part. And here's my move assignment. And so, again, I'm making sure that I'm not assigning to myself. And now B operator equals standard move of D. And now I have these polymorphic functions. We're going to use them. And I have a test function. Notice in the test function, I am constructing an internal D, this compound object D, derived object that derives from a base, and the base includes a composition of C. And I return it by value, so it should move. And so here, let's run it now, and we will compare it to this. Let's run it. Okay. So so the first thing I do is in main is I construct a U, construct a D, and use U. D uses U. And so here I have a U default, C default, B default, D default construction. Now, notice that these print out in the CBD order, but that really isn't their order of construction. I constructed the D, and as its first action, it constructed a B, and as B's first action, it constructed a C. Then C announces itself, and then when that returns, B goes into its body and announces itself, and then when that returns, D goes into its body and announces itself. So it really was constructed in the DBC order, but it looks here like it's the other order, but it isn't. It's really DBC. But you know, that's the mental model. When I call a D constructor, as its first action, it initializes as bases and it initializes as data members, and then it goes into the body of its construction. Okay, now I go into the test function. So let's look at the test function. So here's the test function. So the first thing I do is I construct a D. So here's C default, B default, D default, which are really, happening in the opposite order, like we just said. Okay. Now I'm going to return D. So what I'm doing, I'm returning my value. So I'm going to, if I didn't provide the moves, this would be doing a copy into that D. But because I did moves, it'll do a move construction. So C move construction, B move construction, D move construction. And now this temporary D is going to be destroyed. D destruction, B destruction, C destruction. And now I do this assignment right here. So now I do D move assignment, B move assignment, C move assignment, and then DBC destroy. Okay? Cool. Now, just to show you that you can, I say D of D3 equals standard move. Now, understand the standard move doesn't move anything. It's telling the compiler treat D as a temporary. But now, when the compiler sees this construction from a temporary, it does a move construction. So That's what's happening. Starting a move construction, so I started a copy construction, and here's my starting the copy construction. I copy, copy, copy. Now I'm starting the move construction, and here starting the move construction, and so here's my C move, B move, D move. Now I'm going to do a little polymorphic fancy footwork. So here I have a base pointer that points to a base object, and I call G, and I expect that to be the basis G. And now I rebind that pointer, because it's a pointer, I can rebind it. I rebind it to this derived object that I created above. Now I call pointer to G, and I should invoke the derived G. So let's see what happened. So here's my base object being constructed, C default, B default, okay. And now calling B of G, and now calling D of G. Okay. This is just, this statement, this C out, came from inside this G. I wrote that enunciation inside that G. Okay, let's go look at that G. Here's the derived G. Where did my derived G go to? D. Oh, right here. Here's my G, and so put message calling D colon G. So it's inside that function, that's why we see it. So it's proof that we called that function. So that's polymorphism at work. And now, at the very end, I say leaving main scope. So now, you don't see anything here, but the compiler has written code in the termination code that's called after you pass through that last curly brace, it's going to destroy everything. So DBC, 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 U destruction. So you'll see that above I have one U, and I have 3 of those objects that are being destroyed. Now this is so a compound object is created from the most derived, in our case from the derived to the base to the composed. It doesn't appear that way from the printout just because the derived doesn't go into its body until those other operations happen, but it is really D to B to C. But in destruction, it's in the reverse order, and this demonstrates it is D, B, C, destroyed. Okay? It's always whatever the order is, and U was the last thing constructed. It was the so for this that's immaterial. For the compound object, I'm always going to construct it from the outer part inward. Remember the object diagram. Here's the derived outer part, then the base part, and then the composed part. I'm always going to construct from the outer part inward, and then when I destroy from the inner part outward. That's what's going on. That's compound objects. So again, I think maybe it would make a whole lot of sense for you to walk through that with a debugger and convince yourself, yeah, I really understand what's going on. So, and understand that these compound objects we use all the time. Think about your project 1. You use compound objects all over the place. I did. I didn't write a single move operation. Does that mean I don't care about speed? It means that every single one of my classes had used bases and members that had correct value semantics. And so I didn't have to supply them. And they were there. And they were used just like here. So it's fast, but I didn't have to supply them. And, you know, 80% of the time when you write classes, that's what you're doing. You're either using containers, STL containers or strings, or primitive data. And as long as you do that, not only do you not need to, you shouldn't provide those operations. Why shouldn't you? Because I don't want to write all those, you know, all that code we just looked at in the compound object, all those standard movement, you know, forcing the moves to happen. I don't want to write that code if I don't have to. But I wrote this so I would know how to do it when I do have to do it. And I think you should, you know, you should have a thin little notebook where those few things you got to refer to all the time is right under your elbow. Okay, copy that compound object out and put it in that thin notebook. And on Tuesday we're going to talk about, you know, I'm going to talk about dark corners of the language, and there's surprisingly few for such a big language. You'd expect there to be a lot of idiosyncrasies and funny things that can happen. There aren't that many in C++. C++ was really pretty well designed. But there are a few, and we're going to talk about them on Tuesday. Most of them are associated with inheritance. Most of the dark corners are associated with inheritance. So, and I have a little tiny document, again, you can print it out, that walks you through each of those. Before you walk into an interview, it'd be a good idea to look over that little thin document. Interviewer says, get up at the whiteboard and write a little bit of code that does this. And he'll be looking at it and saying, are you passing by constant reference? Are you being very careful about returning by reference, probably returning by value? And you will, as you're doing that, you will say, well, I'm returning by value because that object becomes invalid as soon as my function ends, but I would write a move constructor to make that efficient. And the interviewer's lips will turn up into a big smile, okay? If you don't, he'll say, thank you, goodbye. Okay, so. I think most interviews, even if you're interviewing for a C# or Java web developer job, they're likely to ask you some questions about C++. I've had people, maybe not in your case, but I've had lots of students write back and say, you know what, they did ask me some questions about C++. The reason is that they understand that if you really have a handle on C++, not a naive, oh, I know what a class is, but you really have a handle on the language, you can get a handle on any language. Right? I promise you, I've probably gotten 20 emails that said, you know what, in that interview, I was interviewing for a web, but they did. They asked me about a virtual function pointer table. They did. So Jessica is skeptical. She doesn't believe that, but wait until your first interview. Okay. And I hope you'll say, yeah, he was right, and I was prepared. Instead of, oh, gee, he was right. I wasn't prepared. Okay. So where are we? Let's see what we're going to do here. Yeah, I got one last thing. Well, I killed the wrong thing. I got one last thing I want to do here. Get out of my face. I want to talk about casts. So I have some time and we'll fit it in today. I want to talk about casts, and let's pull up Visual Studio. And I had it up this morning, so let's see if it's here somewhere. New cast. Yep, it is. So first, let's just look at this sheet. There are 4 new casts: static cast, const cast, reinterpret cast, and dynamic cast. What static cast does is it almost always calls a construction. When I cast, it calls a constructor, almost always, when I do a static cast. If I'm static casting a pointer, it doesn't. It's just moving a pointer up and down a virtual function pointer table. But any other time, I'm really calling a constructor. So for example, in my string class, I had a promotion constructor that promoted a literal string to a Jim Fawcett str. If I did a static cast on that string to my my string class, it would work, would return a Jim Fawcett string, and that wouldn't work without the static cast, without a cast, because I had typed it as explicit. So you got to cast it one way or another. You can cast it so actually I'm wrong. So I can't cast the literal string to a Jim Fawcett string because literal string doesn't have a cast operator, but I can cast a Jim Fawcett string to a literal string, and so that's the static cast will do that. Const cast removes constantness from an object. And you should never use that, except when you pass, for example, in a function, you pass in a string by constant reference. I do that all the time. And let's suppose that I want to call a function from the Windows API that needs a string, needs a C string. The compiler won't let me do it because it doesn't know that that function won't change my object. I know it won't, but the compiler doesn't know it. In that case, I do a const cast to tell the compiler, trust me, that function I'm going to call won't change it. But don't do it if you're not absolutely sure that the function won't change, because the const in the signature of the function is a contract. You're making a contract with a caller that you won't change that object, the parameter that was passed in. And so don't use const cast to let it change the object. Wrong thing to do. Because notice that I passed that string in by constant reference. So if I cast away constantness and I really change it, it'll change it out there in the caller scope, even though I promised him I wouldn't. But when you're calling a function and you know that from the platform API or for some other library that didn't use constant, didn't pass it as a constant argument, if you know it won't change it, then use it, but otherwise don't. Reinterpret cast. Treat an instance of one type by the rules of another. It doesn't change a byte in that object, but it tells the compiler, treat this as this other thing. And that's usually high evil. Intern programmer. It's not compiling. Reinterpret cast to get it to compile. Beautiful source of bugs. Beautiful source of bugs. Dynamic cast is a way of safely, remember in my virtual function pointer table demo that example I gave you, the derived class implemented a member function MF3 that wasn't part of the base class protocol. And I said you cannot access MF3 from that base pointer. So now I want to access that. I want to access MF3 through that pointer, but I can't do it as a base pointer. So dynamic cast allows me to change the type of that pointer. Same address, but it allows me to change the type of that pointer to a derived, but it only succeeds if that pointer really is bound to the type that I'm casting to. So if it's not bound, it'll return a 0. So as long as I check the 0 before I try to use it, it's safe. It's a safe downcast. So now you say, yeah, but look at all these. Why would I ever do why would I ever do reinterpret cast or whatever? Why wouldn't I just say paren blah? We've been doing that for years. Casting is a rich source of bugs. Let's suppose I know in this 100,000 lines of code that I made 3 or 4 casts. I know I didn't make more than that. And I use the traditional form. And I say, okay, let's find them. How do I find them? Well, the only thing I can do is search on paren. And so I get back, instead of 3 or 4 items, I get back 468. Every function, every for statement, every if statement, every while statement, they all come bounding back at me. So those 3 casts are buried somewhere in those 453, or if I'm unlucky, 10,548 things. But if I've used modern casts, I search on _cast, bam, there they are, and only those. But there's another reason. That's one really good reason for using the modern cast. Here's another reason. Casts have these 4 meanings. They always have. The problem is that when I use traditional casting, the compiler has a very arcane set of rules it uses to decide what kind of cast to do. And if you look at Strausser's book when he talks about the modern cast, he says, I don't understand those rules. Now, understand, he's the author of the language. I don't understand those rules. Really, they're very complicated rules. So this way, you get to choose. If you say static cast, it's going to do that. If you say constant cast, it's going to do that. So let's look at a little bit of code. Do we have time? Yeah, we got time. Let's look at a little bit of code. So here's new casts. So I describe the syntax for each one. Creates a new object using promotion construction or cast operator. It's using a promotion constructor typically. May use a cast operator. So I have a from object and I static cast to this type, and over here I've declared this type to object. So that is converting, it's creating an object from the data that's in this object according to what the cast operator does or what the promotion constructor does. Const cast casts away constantness used when you know a function call won't change the invoking object or parameter. But the compiler does not know that, so the way the syntax is, I have some const type, and I say const cast reference of that to this non-const type. And now I can call this non-const function with a non-const type, and the compiler will allow me to do that. But again, don't do it unless you're positive that this non-const function won't change NCT. Because you have a contract with your caller that you won't change it. Otherwise, it wouldn't be const. Reinterpret cast. Reinterprets an object as a different type without changing any of its bits. So here, this is a trivial case. Well, not so trivial. So here, I have a double. D here is a double. And I'm going to cast this to a byte star. Here I have, this is I had redefined a byte as char, and so I should have made this byte star and byte star. But that's what the syntax looks like. Nag, send me an email, remind me, and I will fix that little, I should have used the same type there. And used to test if a pointer or reference to a base type is really a claim-specific, pointing to a claim-specific derived type. So let's look at some cases. So the static cast, so here's a class 2 type with an explicit promotion from the type to type, okay? So now I have to explicitly say I want that cast, otherwise it won't work, it won't compile. And so now here's my class from type, and here's where I'm demonstrating it. So here is the syntax. So static cast to type from object to object, okay? And you know, you can walk through it with a debugger if you want and see that it really is doing what's expected. Here's a const cast. So here I'm passing a string in by const reference, and now I say not const string but string reference equals const cast of string reference of s. Okay, so I've cast away the constantness of this original s to be non-const string, and now I send it to this display function, and it turns out if you look at the display function is just sending it to cout, it's not changing the string. Okay. Here's the reinterpret cast. So I have type def char byte. So I should have made this byte just to, so it's really clear. The syntax is really clear. This clouds the syntax a little bit. So this is really byte star to byte star. So, but I'm passing in a double. And I'm creating a byte array out of that. You know, for I equal 1, size of D, I keep pumping these into the byte. Why on earth would you do that? Because I might want to serialize that double. I might want to send it over a socket. Or maybe I want to write it into a record in a database. Maybe I'm a database manager and I have a record that holds doubles, but the type of that record is just bytes. That's all the you know, because it's just, you know, it's using the schema to say this field of the record goes here, and this field of the record goes here, and this field of the record goes here, and it's managing all that in terms of bytes. But I want to write that double value in, so how do I do that? I reinterpret cast to a byte array, and I write the bytes in to the byte array, to that byte field. Okay. Any other use? So we use reinterpret cast for packing and unpacking things. Packing bytes of something, some other structure, into an array of bytes, and unpacking them back into that thing. Dynamic cast. So here I have a base type and a derived type, and now I say base B, derived D. I have a base pointer that points to a base, and I have a base pointer that points to derived. Perfectly legal. This is just polymorphism at work. Perfectly legal for me to assign a base pointer to a derived object. Okay. And I have a derived type pointer. Now, if PD equals dynamic cast of derived star of the pointer to base, B1, okay, this will fail because B1 points to the base. So this would return 0. But if I made it point to, if I passed it pointer to B2, it would succeed. So this would fail. And I think if I wrote my code the way I meant to write it, I also have the case that, yeah, so here's, if PD, now I'm pointing to PB2, a base pointer that does indeed bind to a derived object. So PB2 is this base pointer binding to a derived object. So this one will succeed. Okay? So if we run it, so here's my first dynamic cast. This is base MF1. Dynamic cast pass, this is derived MF2. Just like we said. And here, reinterpreting double equals 3.145 as byte array, and I just display the byte array, and it's some sort of garbage, you know, out comes the garbage. it would have been interesting for me to unpack it and put it back in that derived type, and that would be easy to do. I didn't think to do that. But, you know, it's just a matter of taking that pointer to the real double, or declaring another double, making a pointer to it, and now reinterpreting that into byte, and now I'm just loading my bytes into that space. So contiguous memory, where that derived is, and as long as I put those bytes in on the same order as I took them out of the original double, it'll work just fine. I pack it and unpack it. We use that for serialization, sending stuff over sockets and things like that. You will use, probably for project 3 and 4, as a starter at least, a communication channel that I wrote, and that communication channel sends binary data exactly that way. Okay? You're going to be asked to send files. We didn't say there were source code files. They might be binary files. You're going to be tasked to send them. Okay, there will be a help session tomorrow. I'm going to talk about my solution to project 1, and I'm going to talk about project 2. So if you'd like to hear about either of those two topics or ask questions about either of those two topics, I'll see you tomorrow morning at 9 o'clock in this room.
In the last of your demonstration code, the main function, there is you declare a pointer. If you declare a pointer here, this new
To a base.
you have not delete.
Yeah, it's a demo. I should have. I have a memory leak.
But if I delete, I say this in here and I run it, it will fail in this place. It will not go on and it will die here.
Mine didn't do that. Mine ran to completion. So, but that, you know, it could be. So let me just pull up. Let's pull up. Let me go back to screen. So let's pull up compound objects. I'm gonna run it. It just ran to completion.
So so you have not deleted the pointer PPR.
So probably not.
Yeah.
So here I didn't, and I should have.
So if but if just as I displayed, if you delete it here, it will not going on. It will die here when we'll delete it.
How do we miss me now?
I'm wondering what can it happen? Or is this?
You're saying if you did delete it and then it caused the program to fail?
Yep.
Oh, I know why. Of course. The reason it caused it to fail is I am pointing to D, which is is not on the heap. It's in static memory. So you call delete on something in static memory, and that absolutely will cause a failure.
So
That's a memory access violation.
does it mean that I need to do a rebind?
You only no. Well, no. What it means is that I should delete this new pointer here before I bind it to D. That's what it means. Okay. So I should have done this. I should have said delete PTR. Okay. And now it'll work fine.
But
then, how does this part work?
I still have pointer defined. It's still declared. Okay. Still has a slot. And now when I do this, I fill it with the address of D. Okay. Let's run it. See.
他说不能在最后delete。
Just fine. The whole problem that you had was because you were deleting a pointer pointing to static memory. You're not allowed to do that.
But it doesn't, just as you just run before, it doesn't, when you delete the PTR, it doesn't say that, didn't say it called the destructor of the B and C. I think I have. Why it does
So
not call?
here, when I deleted P